The first presentation is by Professor Charlotte Krawczyk. She's a professor at GFZ Health Center Potsdam, that is the National Research Center for Earth Science in Germany. At the center, she's the director for scientific programs and the director of the Department of Geophysics. She got a PhD in geophysics from GeoMar and Kiel University. Lotte's areas of expertise include seismic method and technical developments in applied geophysics. And applied geophysics, geophysical imaging of the formation and mass transport, sub and seismic deformation analysis, and geodynamic interpretation. To start this workshop seminars, Professor Krawczyk will present a lecture entitled Fibre-optic Strength Sensing in Urban Environments, New Possibilities in Hazard-Prone Regions. Thank you, Lotte, and you have the floor.
Thank you very much, Dante, and also all the others like Eileen and Nate in the first instance, providing us with that workshop opportunity. I will try to share my screen and start a lecture that will show you some of the ideas that we are developing currently with measurements that we are doing from Potsdam. And as Dante described, so what he said in words, you see here on the first slide, once that appears, I hope soon, on your screens. So I'm mainly a seismic person, but did in different environments, in different depths and areas. And in fact, it's like with many of us, we came from geodynamics and worked towards surface because we know that there are important tasks that we have to tackle, and part of that will be that we discuss fiber-optic strain sensing. This can be an especially nice tool and useful tool if you go to hazard-prone regions. And what I would like to do on behalf of the work that I do together mainly with Philippe Jousset and Thomas Reinsch, also collaborators in GFZ, driving different themes forward, is to give a short motivation and some principles concerning DAS. Then I will give experimental setup and case study results before we come to conclusions and outlook. So it's really, for me, it's really, I appreciate that I can start off this workshop and also being in the steering board of this RCN, where we share ideas and which really helps a lot growing these networks. And while I'm starting off, I will give some principle motivation and also measuring principles to enable all of us to dive into the days that we could spend together. So if we go for motivation, we see that we need field sensor densification also to study all kinds of spatial-temporal processes. And for instance, what was done in seismology for more than 10 years was having moving sensor arrays as US array, covering the entire US. Or in Europe, we had started working on Alp array, which also covers the alpine mountain change in its complete entity, both onshore and offshore. And there it's really a challenge to bring together scientists from different countries to have funding for such a network and put up all those stations, which are roughly 500 and even more, at the same time, so that such networks can start registering. And for the alpine mountains in Europe, it has a span of roughly some 1,000 kilometers and also an altitude up to 4 kilometers. And this means the conditions bringing out those networks and arrays is not that simple. And given that, it would be great also, in addition to many other studies that work with large N and many nodes, to have some new clues on that and to make that part of the life easier. If we now look at what this sensor array is capable of doing, I'd like to show you this small animation, you see here the map again with all those stations that you had seen to the right side. And at the same time, we will have now a look how these stations recorded a large distant earthquake that came in with a magnitude of 7.5 from Honduras. Thus, it will reach this array from the west, which means here on the slide from the left side, and there it arrives earliest. So after this large earthquake occurred, it was registered roughly 20 to 40 minutes later. And what you can see here, that both P and S waves run through the entire array, and then when the surface waves come in, then you see there's a lot of music in this array, and this is something we would like to understand and that we need to understand. So to see how the wave trains run through an array, how they influence with different wave types the entire region. And finally, what would be great to learn is not only the processes taking place in the shallow and deep subsurface, but also how do local earthquakes occur, what are their processes, and how can we analyze the entire wave field. So not just looking at onsets of the wave field like we do have here, but also to look how this entire wave train runs through an array. And this could be, as we hope, much easier if we apply fiber optic sensing technologies. This always means, as you might have read, using a fiber optic cable just from telecommunication, connecting it with an optical source, transmitting light, and then somehow analyze something. And this somehow analyze something, this needs to be defined. So we have physical phenomena within the cable, and then we have different possibilities to study that what happens in the cable. So we can observe the transmission of information in the cable with a light and use those telecommunication technologies. We can use single, specially designed sensors, which are used for mainly point sensing. So we have specifically designed optical components that we try to reach with a laser pulse and then do measurements by that. And then there is a distributed sensing, which means the entire fiber is a sensor. So we always have to differentiate point sensing and distributed sensing. And the distributed sensing, that is what comes closest to what we had seen before in the conventional setup of seismometer stations to monitor how a region is deforming. Now, if we have a look on what we can do with point sensing and distributed sensing, we can yield quite different characteristics. So it can, on the one hand, be temperature, pressure, but also what we are most interested in the next day, strain and acceleration and the orientation of a signal. At GFZ, we work in different disciplines, and if you have a look to the left, we can touch fields like rock mechanics, seismology, of course, then all what comes with the field of hazards. We learned a lot from studying how fiber optic sensing was introduced for wellbore integrity measurements and also for reservoir processes and most lately for environment. So a lot of this technique was really developed in that sense from physics, from material science and reservoir engineering processes. Now, how does it work in principle? So we have an optical fiber, and this fiber is made of glass. This glass is extended so that it builds up a fiber, and during this process of manufacturing a fiber, we have some, let's say, sort of inconsistencies within the fiber, which is marked here. I try to find the laser pointer. So these inconsistencies, they are marked here and indicated as black dots within this optical fiber. You see here that such a fiber is really tiny and small, and you have it coated. This can be by plastic, by material, by liquids. So there are different opportunities and possibilities. And once a laser pulse is sent into this fiber, as it's done with most of the facilities that are available on the market doing those measurements, we see that the coherent laser pulse is sent, and then at these inconsistencies or null points, we can have elastic Rayleigh scattering. So if we send in further pulses that are coherent, they can meet one of those points and then be scattered back. This can happen to any of those inconsistencies in the fiber cable. And by studying how this intensity of backscattered signals and also of possible phase shifts of those signals, we have an intensity time or length graph where we can see how these pulses are coming back, being reflected from those different scatter points along the entire length of a fiber. And this is what makes the distributed sensing. Assuming that these points are stable in location, then we have one graph. If there is a lengthening of this optical fiber, then the position of the different points to each other changes, so it can be smaller or larger. And by this, we have the position of strain changes along the fiber that we can observe by those coherent laser pulses. And this gives us an immediate measure of the change in intensity and time, thus a change in strain by time and the strain rate. So this is one opportunity to measure strain rate. And if we integrate that over time, we can determine the local strain. And to know about the local strain is of immediate importance for many questions we want to answer, not only about earthquake hazard or volcanic hazard, but also about infrastructure safety and things like that. Now, what we need also to define always is a kind of transfer function. The cable, imagine, is buried in the ground, and we need to study how well is the cable coupled to the ground and how well can we see the signals. So it's again, the question, what can we interpret? How much noise do we have on a cable? Or do signals that look like a signal are perhaps, are they caused by bad coupling or any other thing? So the basic assumption that we do for dust is that the scatters in the fibers are densely distributed, that they are randomly distributed, and that they are stationary in time. That was done first was to measure temperature variations in boreholes. That was one of the real big steps on using fiber optics for temperature sensing. And nowadays, it's mainly used also and developing rapidly for seismic investigation. The terms that you will always find when you read through also the references that you can see at the end are pulse length and shape. This is important to know about the incoming signal into the fiber as such. And then you can also define with the system with that you measure what is the interval for which you will have a look at how much frequency of phase shift will occur. This is the so-called gauge length. So this is the interval for which you interrogate your cable. Typically, it's 10 meters. Often we try also to use smaller sizes. That depends on the wavelengths that we want to discover. And shifting this gauge length and the observation successively through the cable, this is the sampling with that we interrogate the cable. Now, having said all that and introduced into the motivation and the principles, we can see that the distributed acoustic sensing using the fiber itself as a sensor has a lot of advantages. So we have no predetermined points like we have to do with seismometers or geophones. We can do the acquisition along the entire length of the cable, and we have a very dense spacing. The measurements can be continuous, real-time, and given by the manufacturers of the cables can also allow for harsh downhole conditions so that we can measure up to roughly 300 degrees Celsius. If that measurement is connected in addition to remotely operating systems, we can have readouts at any time and also check what our cable is doing. So the advantage of that is there, and we try to develop detailed structural images of the subsurface using these. We also try to monitor the parameters of the subsurface reacting on deformation and try to learn about process understanding of signals we perhaps might not have seen in any currently available seismometer. Having said that, I would like to go now to a case study that we performed in Iceland. Iceland, yeah, is an island in the active rifting zone in the northern Atlantic. It has a lot of seismicity as marked here by the red dots, and we can see the rift zone running through the entire island and also strong deformation marking the active rifting. A lot of volcanoes are also connected to that, and there is really geodynamics at surface. We studied this southwesternmost part of Iceland, which is the Reykjanes Peninsula. And if we have a closer look, we used there a seismic network that was set up here along this line. And we have broadband seismometers for studying and also geophones marked here with blue dots along the red line. And the red line is an old buried telephone line from the Iceland Telecommunication Company that we were allowed to use. So this is the network to study with. And this is how the broadband sensors with their registration unit look in the field. And also the 3-component geophones that we can see here also being brought out. The entire line was roughly 15 kilometers long, and we will zoom in now in this part where we see we also have surface expressions of this river rail faulting with a lot of fault traces that we can mark along here. And there are different lava flows bringing in old and younger layers of lava from the rifting process. And this is the area of interest we have a look now. So there, this telephone line, again, this red line here, crosses an active fault zone. If we toggle force and back, we see that also here at surface, and the incisions in the field look like this. So we have here this fault zone that we had seen here on the aerial photo, and we can see that quite nicely in the field and also the second one coming in there. The telephone cable crosses this zone in here, and we had a closer look to that later on. If you use a variable cable that had not been mapped that well in former times, you need to locate the dust line. This is always necessary to know where you record your signals. And so in that case, we knew it's somewhere along this road. And what we did then was to provide one geophone and a registration unit, a cube, and also a hammer-blown seismic experiment here to do that several times. And by that, we could locate the more exact position of the cable that is underneath this dam along the road here. So it works like this, that you can just have this base plate for the hammer shot. Here you have the geophone and the cube. And you see that if you do it as normal hammer seismic, you can have active signals and record them by the geophone and in addition by the cable. This is how it looks afterwards. So we had here at a certain distance, if we look at the vertical axis, so we have here kilometers and here we have the current time. There where the signal is closest in time, there we have the geophone, and here we can see it along also the cable. And by that we were able to find out where in relation to the position of the geophone lies the cable underneath. Now, we did that several times, and as you see here, this is a distance time plot, and now see that these are larger distances, so this is 1 kilometer, and we have the time here in minutes, and you see a certain pattern along the entire section. That what we discover in here is a track of 2 cars. So 2 cars went in the field. They moved along the cable because the cable was parallel to the road, and then the car stopped, brought out the hammer shot experiment tools, and then these are the hammer shots that we had just seen on this detailed view before. And this was done several times. So the cars continued along the road. They did the hammer shot experiment as well, brought in all in the cars, went along, and so on. So this we did all along these 15 kilometers to locate the cable. This is an exercise, might appear perhaps rather boring, but it brings out great data also for active shots. We were lucky that we could record a local earthquake below the cable. It was a shallow earthquake located by the Icelandic partners at depth of roughly 3.5 kilometers only, with a magnitude of 1. And what we could record in the cable is that what you see here in this image. So it's a distance of 2 to 12 kilometers along the cable. Then here we have the time in seconds, it's roughly 4 seconds. And then we have a clear onset here first of the P wave, and then later on of the shear wave. So this is more or less comparable to that what we would expect if we have an earthquake signal or some source signals that we record also with seismometers. The difference here is that we have a very minor P wave and a very strong shear wave. This is due to the directivity along the cable. So the cable is most sensitive along the horizontal line, of course, and this is why the shear wave is here given with large amplitudes and the P wave only with small ones. So this is something that we had to learn newly, that this is different than we were knowing before when we go with 3 components or vertical component seismometer. We can display also these amplitudes in here, and then we have that what we would expect if we would have amplitude time plots. We used all these data to go along with the localization of this earthquake. What we need is, when we record these data, is a velocity model, because we have to integrate the strain rate to strain if we want to see that, and also for localizations, we need to know about P wave and shear wave velocities. This was known from some colleagues in Iceland, so we used an older model that was measured by a seismic station network for a decade in 90 to 2000. And thereby the earthquake was located at 3.5 kilometer depth. We tested the localization also with less cable data only, and did automatic picking for all traces with P and S. And what came out after this was that graph you see here. It's a time distance plot again, and with the symbols marked in gray, we see all the signals for the shear waves, and the symbols marked in black colors, they show the P wave. And we see after these 3000 pics had been picked automatically, we see clear lines that we can see for both signals, for both wave types, and we can compare that, what we know from the DAS cable, with that, what we know from the geophones that were paralleling the setup in the field. The synthetic line then gives the mean value along this. If you use that further, as you do for hypocenter locations, you can do a grid search, and where you have the smallest root mean square error, in this case is 0.5, there you would locate the earthquake. And that fits quite nicely along the cable, the black line in here, with the location that was done by the seismologists on Iceland. So we are quite confident that also with this routine that we applied to the strain sensing data, that we can also, if they happen below the cable, locate quite nicely also local earthquakes. It's possible to locate both local and also distant earthquakes, for sure.
Noted. Dante.
Yeah, I'm almost done. Yeah.
Okay, perfect. Thank you.
Yeah. So if we, do you hear me again?
Yes.
Yeah. Okay. So if we look at this in a monitoring scheme, it looks like this. So we have here the cable, and then the earthquake occurs, and then it influences the entire cable, and you can monitor that. Here you have 10 seconds that run through, and this can be done along the entire cable and many other experiments. So if we compare the different sensors, we also see that this, especially in 0.1 to 100 Hertz spectrums, that these different seismometers, geophones, and also DAS cables, that they fit quite nicely and reliably might produce the same quality signals that we want to see. Now, at the end, we can also use these data for seismic imaging. So the cable crossed the fault zone, we see it in here, and here the earthquake came in, and then once we see here these reflections, we can also infer that they run further, and by that we can see hidden faults that we could not see in the field before and that stop below surface. So this is also a very interesting tool that can be used also in volcanic areas where we bury by hand fiber optic cables, and where we can observe, in addition to explosions that are seen, so a different sort of natural hazard, where we also can register with this cable those signals that we are used to interrogate. So having given all that, the achievement that we have is that all cables are usable, that they have a broadband character, and that we can detect many interesting things by that, and also in areas that are industrialized and urbanized. This here is a typical crisscross pattern from car traffic during the day. So you have these cars, depending on in which direction along the cable they drive, and completely different to now this, how it looks in my office just now. You see there is almost nothing because it's the workshop time in the evening where there's no any longer car traffic. With these achievements, we also buy a lot of massive data. We will hear about that later on today, and we see that despite these massive data and new processing tools we need, that we also have to answer single component and coupling issues. The opportunities for monitoring applications are widespread, and also later on we hear about earthquake hazards, but also for hydrology, offshore exploration, infrastructure monitoring, and many other tasks. This seems to be a very good tool that is on the market now. And with all of that, I would like to thank you for your attention and invite you for further reading. And I would also point that there is this data set available on the website that you can grab from there and also make your first steps analyzing this sort of data. Thank you.
Thank you, Lotte. Thank you very much. Very good. I feel bad that we can't have a round of applause, but if you will, I'll give a round of applause in your offices and on your desks, if you will. Thank you. Lotte, we have quite a few questions. I'm not sure we're going to be able to get to all of them, but I'll try to organize them. This is Scott Tyler again. I'll try to organize them in a little bit of maybe less complex to more complex. So there were a few questions that began a little more understanding what the gauge length, how the gauge length is defined, and also even a little bit more on how are we measuring if we have scattering sites through the fiber and we are pulsing the laser at relatively high frequency. How are we discriminating between pulses of light coming back from different scattering sites and different pulses coming back? So a little more perhaps on how the system actually is working. And I'll also point our audience to the introductory videos that Nate Lindsey and Eileen Martin have put together to go a little more into detail on kind of the details of how it works. But maybe Lotte, if you could go back to one of your early slides and just walk us through.
So we will be there quite soon.
Yeah, that's okay.
This is much easier. Yeah, there are different systems in that sense on the market. So what you need to do is to connect your laser facility with the fiber. So you need to splice in an extra fiber in that sense that allows the transmission of the coherent laser pulse into that fiber. You have a high frequency of this signal that is pulsed into that, and it has a defined wavelength and a defined pulse shape. So you also can vary the shapes. What you have to decide, this is, yeah, as you do always when you go to the field. So you have to decide what is roughly the wavelength of the feature I want to see. And given then the nuclear theorem that tells you, okay, the resolution would be perhaps maximum half or a quarter of the maximum wavelength, you have to tune the pulse length and the shape of that. The gauge length in some systems that are available is set to 10. In some systems, you can change the gauge length. So this is also something that is currently developed because these systems are new and there are a lot of companies developing their own lasers, their own sensitivity tools and so on, and also to allow the user to apply different gauge lengths. So this is part of the development currently done. So typically these 10 meters, they are good to record quite nice nanostrain patches in the subsurface. If we want to see even smaller effects, like let's say sinkholes of a diameter of 10 meters, then we would need a smaller gauge length. With the system that we have so far, we cannot change that to smaller sizes, but this would be something or a wish for the future, where we then also would have opportunities to monitor smaller structures.
Okay, thank you, Lotte. So just maybe to summarize, but the gauge length itself is to some degree a function of the, I'll call it the resolution of the instrument, if you will, both in frequency and also in frequency.
Yeah, exactly.
Okay, good. Thank you. Let's see. We had a question on can DAS signals go through telecom amplifiers? So if you have an amplification system, transmission receiver along your dark fiber, can you still use that?
Yes, you can use it. What you need to know is the exact answer function, and you also have always to correct the signal that you measure for the system response that your system does. So you need to correct that, and also need to have an idea about this amplitude enhancement, and also if there is a kind of phase shift by this enhancement. This is something that is needed to know, but as you do with the system response that you can correct for, you could also correct for that, if that is well known.
Okay, thank you. A question from Carlos Becerril. What could you mentioned channel length. So what is the difference between gauge length and channel length in your presentation?
Channel length, I'm not sure to what it should refer to now. So the channel length, perhaps it refers to that what you see, or for how far or how distant along the cable you will measure. So it's also your decision if you say, oh, I try the entire 30 kilometers of the cable, or if there are also different transmitter nodes in between and you say, okay, I'm happy with the next 10 kilometers because, yeah, the part of interest is below. So this might perhaps be that what was asked, but I'm not really sure about what is meant.
Okay, all right. Sorry to give you a tough question. I think we have time for one more question, and why don't we go, and again, there's quite a few questions. We will try to get all these questions answered post the meeting, so don't worry, we will get your questions answered. You mentioned, I think in your talk, that from DAS there might be better quality S-wave picks, and Bruce Howe responded that there is, I think, a review of that. Could you explain that a little bit more?
Yeah, so what is interesting to see is that we have both shear waves and P waves. And the shear waves, they are especially important if it comes to hazard, because as soon as we also have strain, these are important to know because of derived shear wave velocities or the potential by incoming deformation to shear an area. And what we see here is that we have strong shear waves imaged, at least with high amplitudes, because the directivity of a cable is horizontal. So we have this, in that sense, coil pattern, how the energy is transferred in seismic sensors. And this also happens here. If we would do a 3D setup of telephone cables, then we would have also other waves as we do in board. There you could have also a strong vertical component as a P wave. So as long as we just in the horizontal, we have strong shear waves. And if we would do that in 3D and not as single component sensor, then we also would have stronger P waves.
Very good, thank you. All right. Latte, thank you very much for your presentation. I think we're going to take a 10-minute break according to the schedule. So we will try to get your questions answered as we go forward here. And so Latte, stay on the line and we can keep you answering some questions, and we will get those posted. So thank you all. Thank you, Latte. And we will take a 10-minute break. We will reconvene at 5 minutes past the hour. Thank you.